The very first step in any problem involving Newton's laws is always what we call a free body diagram. So free body diagrams, when we apply to Newton's second law, the sum of individual forces, remember, is going to be equal to the mass times the acceleration. Well, we need to isolate. You need to isolate the object. So isolate the mass m, meaning that you're going to separate it from its surroundings. So let's say, for example, I have, a box on a ramp. Then in that case, I might draw not so much the ramp, but I can just draw the box of mass m. Or if it's a box in an elevator, I might not tilt the box and I might just have, say, a box of mass m like this. But I'm just isolating my object. I'm removing it from the rest of the picture. That's the first step. Then, because I want to isolate these individual forces, I want to draw the individual forces that we just came up with. We want to see our list, right? That we just made a list of ones that are allowed. We want to draw our individual forces acting on that one object, on that one mass m, not on anything else happening. You're just imagining, what if you are that mass? What forces are acting directly on you? And to do that, you're going to draw arrows pointing in the correct directions. And when possible, you want to draw these to the correct relative scale. So for an example, for the box on the ramp, I might have my object here, and then I'm going to have a downward force of gravity, which you can write as F sub g. You can also write that as mg. And then you're going to have a normal force. If there was friction, I would also add that in and it would act parallel to the ramp, but we're not doing friction yet. So that might be what my free body diagram looks like for a box on a ramp at this part. If it was a box that's just, say, in an elevator, sitting on the floor of an elevator, then I might have a downward force F sub g, which again equals mg, and then say an upward force from the contact between the ground and the box. So I'm going to draw those individual forces. Now, there's a couple important notes here. You're never going to put acceleration as a force. Acceleration is not a force. And you're never going to put ma, which is the result of a net force, but not a force itself. So never put ma as a force either. Neither of these belong on the diagram. Only use forces from the list. So that's our basic free body diagram, but to make it useful for problem solving, there's two more steps. The next step is going to be to identify if the acceleration equals 0 or not. And then label the acceleration as a double arrow near but not on the diagram. So if I go back to these diagrams here, then let's say that this block was sliding down the ramp, which is exactly what would happen if there was no friction. Then near, but not on the diagram, I'm going to draw that downward arrow, and that would be my acceleration. If my acceleration is 0, I would just write a equals 0 instead of drawing the double arrow. Here, let's say my normal force is less than my weight. And we'll see in situations when that could happen. Then I would have an acceleration that would be downward. So my acceleration would point down. So I'm adding that to my diagram. And again, this is exceptionally useful for problem solving. The next and last thing for a free body diagram is to put an axis near but not on the diagram. And so when we're doing problems, we have to know what we're defining as x and y axes. And so if I have the block on the ramp, an interesting thing is that I can tilt these axes. I'm allowed to tilt the axes. So I would go to this one, and then I would maybe say, okay, I'm always going to want to take one of my axes so that my acceleration is 0 along that direction, so perpendicular to the ramp. So I would maybe call this my x and my y axis. You can choose whatever you want in terms of whether you call positive x to be down the ramp or up the ramp, but I just choose a right-hand coordinate system. And so this then would be my completed free body diagram, where I have drawn the individual forces, identified my acceleration near but not on, and made an axis near but not on. For the elevator case, there's no need to tilt my axes, and I only have a single direction. I don't worry about the x direction at all, so it's just a matter of what I'm calling positive y. So it might look something like this, and that would then be my completed free body diagram for the box in the elevator.
So go ahead and pause the video and read through this self-check question, and then at the end of the video, we'll talk about the answer. So the correct answer is in fact C, and that's because it has a normal force that is perpendicular to the ramp. So the case here, we would have, say, an object on a ramp like this. The normal force is perpendicular. It would have a force of gravity, the weight, which points directly towards the center of the earth. It also has the axes, and the axes are tilted so that one axis is parallel to the direction of motion. This is very important, so that we have our acceleration only along one axis. And then also we have drawn the acceleration near but not on our diagram. Acceleration is not a force. MA is not a force. MA is the result of a net force. Those do not belong on the diagram. The only thing that involves that goes on the diagram are the individual forces. So in A, we can see that that is what is incorrect, is that we never put MA on our diagram. That is also what's incorrect about B, and the axes in B are not tilted. And then over in D, we can see we have our tilted axes, we have our acceleration arrow near but not on the diagram, normal force and weight, but then we have our net force. The net force is not an individual force. We're going to do that in the next steps where we'll add up all our individual forces, but the net force never goes on our free body diagram. All right, let me know if you have any questions.